Okay, I want to show you an example. This is a rather clever example of using a line integral to calculate the area of a region. And we start out with Green's theorem, and I'll show you, we don't usually do this kind of thing. It's just an interesting application. I think you might like it. Okay, so here's Green's theorem, right? This is the differential form of Green's theorem. And notice on the right-hand side, we have the partial of g with respect to x. Remember, again, g with respect to x, g itself rather, that's the coefficient of the dy right here. Okay, and the partial of f with respect to y, well, f, that is the coefficient of the dx. Okay, okay, now, recall we said that the area of a region R, using a double integral, looks like this. Well, I'm going to rewrite that 1 as 1/2 plus 1/2. Being very, very clever with it. And then what I'm going to do is I'm going to rewrite each one of those terms like this. Okay, see this 1/2 right here? I'm going to rewrite that as the partial derivative of x over 2 with respect to x. And then I'm going to write minus, okay, and then that 1/2 right there, I'm going to rewrite that 1/2 right there as the partial of negative y over 2 with respect to y. Okay, that makes sense? The derivative of x over 2 with respect to x is 1/2. The derivative of negative y over 2 with respect to y is negative 1/2, and this negative will make it positive. But more to the point, gang, notice that that all of this right here looks just like this in Green's theorem. And I'm going to make a note to myself. That's going to be my g, and that is going to be my f. And so by Green's theorem, I can rewrite this double integral over the region R like this. And if you like, we can move the 1/2 through the integral symbol. Okay, take a look at that. Okay, so now let's actually apply it to something that we already know the answer to. All right, so for example, let's find the area enclosed by the ellipse. Remember now, we made this calculation one time for all time, so we already know what the answer is. So the ellipse is given parametrically like this. And with this choice of the cosine and the sine, we know that the curve is going to be traversed in a counterclockwise sense. And the region it encloses will be the shaded area of an ellipse. So we know that Green's theorem will definitely apply. And so the area then is just simply this. All right, now I'm going to replace that integral and put it in parametric form, 0 to 2 pi, so that's okay. Switch out the letter y now for b sine t. Watch that minus sign now. Okay, then the differential of x. Well, here's x right here. So the differential of that is minus a sine t dt, right? Plus, now the x, replace x with a cosine. I'm kind of running off the page here, so I'll go down here. All right, and then the differential of y is going to be b cosine dt. Okay, and then I'll simplify. All right, so these two negatives give me a positive. I'll have ab sine squared t, and I'll factor out the dt, of course, plus ab cosine squared. Okay, notice we've got the fundamental identity right there. We can pull the ab through the integral symbol. Sine squared plus cosine squared is equal to 1, of course. So the integral is worth 2 pi. The 2's will cancel. Pi times a times b. Okay. So it's a clever way to find the area enclosed by a curve. I mean, it's not the go-to thing to find the area of a region, but I think you'll admit it's pretty clever.